Hi, everyone, and welcome to Statistical Reasoning in-class activity or Lesson 12D, Confidence Interval for a Difference in Population Means. Do you think the font used in printed instructions influences how difficult people think it will be to follow those instructions? Would you rather read a set of instructions printed in Arial, like this font, or in Mistral font, this font? Obviously, if you look at this, it says this is not hard to read, the Arial font, and this is a little bit harder to read, the Mistral font. So I'll give you 1 second to just jot down your ideas right here. If you want to pause the video for a second, please do that. Okay, welcome back. So generally speaking, if I were to look at directions or instructions to do something, I'd rather have it in a font that's easy to read. So again, you can write that down there. Okay, objectives for this activity are you'll understand a difference in population means can be estimated using a confidence interval. There are assumptions, just like in lesson 12C, for a single population that should be checked to ensure that the 2-sample T confidence interval is an appropriate way to estimate a difference in population means. And students will be able to assess whether the assumptions for a 2-sample T confidence interval are reasonably met, and then use technology to compute the confidence interval for a difference in population means when the samples are independent, and interpret a confidence interval for a difference in population mean in context. So in previous lessons, you've constructed confidence intervals for a population proportion, a difference of proportions in a population mean. The form of those confidence intervals always looked similar. It was an estimate plus or minus a margin of error. So when you are interested in estimating a difference in population means using data from independent samples, the confidence interval has the same form. The estimate used to construct the interval is the difference in the sample means, x sub 1 bar minus x sub 2 bar. So again, this is your sample mean from the first sample minus your sample mean from the second sample. So you have to identify which one's going to be sample 1, which one's going to be sample 2. If you reverse it, then everything's going to be backwards, but which is okay. You just have to interpret it backwards as well. So again, one sample is going to be considered sample 1, one sample is going to be considered sample 2, and this is the mean of sample 1, and this is the mean of sample 2. And the margin of error is calculated using a standard error for a difference in sample means and a critical value from the T distribution. You will use technology to calculate the margin of error, so we won't worry about the formula for the standard error or margin of error at this point. You will see them in class activity 13C. So for right now, the app is going to calculate the standard error or margin of error. Compared to the formula for proportions, the margin of error here is calculated a little differently. Instead of multiplying the value by a standard error by a value from the normal distribution, meaning a z-score, it is multiplied by a value from the appropriate T distribution, or T-score. This is not surprising if you think back to your work with the standardized T statistic for the in-class activity or lesson 12B. Okay, in the preview assignment, you used data from a study that investigated the effect of using a cell phone while driving on reaction time. In this study, 64 students were randomly assigned to one of the 2 groups with half the chance, with half chance. So in other words, half the students went to one group, half the students went to the other group, whether they were using a cell phone or not using a cell phone. Students in both groups were asked to drive in a driving simulator and to press a brake button as quickly as possible when they saw a red light. Response times in milliseconds were measured. Students in one group used their cell phones while driving in the simulator, and students in the other group did not use their cell phones. This data set is built into the data analysis tool, and you will use these data to estimate the difference between the mean reaction time for people who use their cell phone while driving and the mean reaction time for people who did not use their cell phone while driving. Recall from previous work that when you want to use a confidence interval, you follow a process that includes deciding what confidence interval method might be used, checking the assumptions for the chosen method to make sure it is appropriate to use, and then calculating the confidence interval and then interpreting the interval in the context of the problem. So number 2, in the preview assignment, 2 sample T confidence interval was selected and you verified that the necessary assumptions were reasonable. Now we will look at calculating the confidence interval and interpreting it in the context of the situation. So part A asked you to go to the Data Center Math Pathways Comparing Two Population Means tool at this URL. So again, you can either go to the clearinghouse, the data, the library that has all the apps, and then find this particular Shiny app, or just go directly to the Shiny app using this link. You will use this tool to calculate the confidence interval for a difference in population means. So under the confidence and significance test tab, select reaction times data set. For a type of inference, select confidence interval and use the slider for the confidence level, select the 95% confidence level. Here's the results, but I'll show you on the screen in a second. Based on the output, what is the 95% confidence interval for the difference in mean reaction times between people who use their cell phone while driving and people who do not use their cell phones while driving? Again, this is the summary from the app that's copied and pasted into this lesson. So let me go ahead and show you how to get this into the app. Let me share the screen. So again, on the DCMP, Data Center Math Pathways Data Analysis Tools, which is a clearinghouse of all the apps you've used this semester, here we're going to find the one that talks about confidence intervals and significance tests for 2 samples, and specifically comparing 2 population means, not proportions, but we're doing averages or means. So this is the link that was given to you in the lesson that we're currently working on. So if you go to this website from textbook, and again, you have the option to say, I already have the data in the textbook. It's a data set that's already been defined, or you can provide your summary statistics for each of the 2 samples, or you can type in the raw data and actually have the individual values. But for this one, I'm going to do from textbook. I'm going to choose reaction times, and it has the 2 individual samples from the populations, one where the person's using the cell phone, and one are reaction times for persons that are not using the cell phone. They want us to identify the 95% confidence level, which it already is defaulted to. And here's your descriptive stats for the reaction times for people who use the cell phone and for people who didn't use the cell phone. Again, there was 32 people randomly selected for each group. Here's your point estimate. The point estimate. Here's your standard error. Again, the standard error is not going to get the formula now. We will talk about that later in lesson 13 in the margin of error. Okay, so the margin of error, remember, is always going to be your standard error times your critical value, in this case, a t distribution. So the confidence interval is going to be calculated as the point estimate. Again, the point estimate is the difference in the sample means. It's sample mean 1, 585.2 minus sample mean 2, 533.6, which produces a difference of 51.6 milliseconds between the 2 groups, plus and minus the margin of error. So 51.6 minus, we always do the minus first, 39.3 gives us 12.3. And 51.6 plus 39.3 gives us 90.9. So here's our 95% confidence interval for the difference between the average time a person hits the brakes when they're using a cell phone and when they're not using a cell phone. So again, this is all summarized on the lesson. I've copied it and pasted it into the lesson. So let's hit stop share. So here is the confidence interval again. So it says, based on the output, what is the 90%, 95% confidence interval for the difference in reaction times? So the confidence interval is 12.3 to 90.9. Just a side note, had you reversed these two guys and made the control group where they don't use a cell phone sample 1 and the ones they use the cell phone sample 2, these would have been on the negative side. So it would have been negative 90.9 to negative 12.3 because everything would have been backwards. Okay. So now it says, think about how you previously interpreted the confidence interval for a difference. How would you interpret the confidence interval you just calculated? So again, for this particular confidence interval, 12.3 to 90.9, we'd say we feel 95% confident that the true difference between the group that uses a cell phone while driving and the group that doesn't use the cell phone while driving has a mean difference in reaction time of 12.3 to 90.9 milliseconds. Okay. So next question, part C asks, what does the confidence interval tell you about the effect of using cell phone while driving on reaction time? And this is in general. So if the interval has endpoints that are both positive, in this case, they're both positive, 0 is not on this interval. 0 says there's still the potential that there's no difference in the means, but in this case, and 0 is not on the interval, we're saying there's evidence, the statistics provides evidence that it takes longer for people using a cell phone as far as reaction time than it does with people that don't use cell phone. Had this been again flipped and it been all negative, and again 0 not on that interval, then again at that point it would just be everything would be reversed. In that case, if the control group was sample 1 and the cell phone was sample 2, we'd say it takes less time for people without a cell phone to react than it does with people who have a cell phone. So let me go ahead and write that down. Okay, so what does this suggest? It suggests that there is statistical evidence that it takes longer, and again, longer because 0 is not on that interval, takes longer for people who use their cell phone while driving than people who don't use their cell phone while driving to react to the red light. Okay. So we'll go ahead and take a second or so to write that down. Okay. Part D. Which of the following is a correct interpretation of the confidence interval of the confidence level of 95%? A, the probability that the actual value of the difference of the population means is between 12.3 and 90.9 milliseconds is 95.9? No. 95% of the people using their cell phones while driving have a reaction time between 12.3 and 90.9? No. If this method was used to construct a confidence interval for the difference in population means for many different pairs of samples from the population, about 95% of the intervals would contain the actual difference in population means. Yes, that's the correct interpretation. And again, what we're saying here is the interval we just computed is one example. This is just from one sample from the from each the cell phone usage and the non-cell phone usage. Had I taken another sample of the same size 64 and split it up 32 and 32, we get different values here. And again, we get 100 cases. If we did it 100 times, on average, 95% of those intervals would capture the true difference, the true mean difference between the values, mu1 minus mu2. 5 of them would not capture it. Whether or not this is the one that didn't capture or not, we don't know. So again, we're using a technique that works 95% of the time. So the mean difference in mean reaction times is guaranteed to be in the interval. No, we're not guaranteed that. So again, the correct interpretation is C. When we use this technique over and over, 95% of the time, we're going to end up with the correct decision. 95% of our intervals are going to capture the true difference of the population mean between mu1 and mu2. Okay, part E. If we use this sample to calculate a 90% confidence interval rather than 95% confidence interval, how would the width of the two intervals compare? Again, as in previous lessons, you saw if you have less confidence, then you have to go out less deviations or less typical errors. So for a less confidence, it's going to be a smaller interval. So the width of the two intervals would be the same? No. The 95% interval would be wider? Yes. The 95% interval would be narrower? No. Okay, so again, the 95% bigger confidence leads to a bigger confidence interval. Less confidence leads to a narrow interval. Okay. As was the case with previous inference methods, there are a few assumptions or conditions that should be checked before using the two-sample T confidence interval. These were introduced in the preview assignment and are included here as a reminder. So again, the samples are independent. Again, what that means is the samples are not paired like a before-after experiment. The two populations are completely independent or different populations. So they're not paired. Okay, each sample is a random sample from the corresponding population of interest, or is it reasonable to regard the sample as if it were a random sample? It is reasonable to regard the sample as a random sample if it was selected in a way that should result in a sample that is representative of the population. If the data from an experiment, you just need to check that there was a random assignment to experimental groups. So for this one, we had 64 volunteers and they were randomly assigned to a group where they're going to use the cell phone and one in the group that was not going to be using the cell phone. So this substitutes for the random condition and also results in independent samples. For each population, the distribution of variables that was measured is approximately normal, or the sample size from the population is large. Remember, for means, we say that a sample of size 30 or more is considered to be large. We had 32 from in each of those groups, so our sample was large enough. If a sample is less than 30, again, you need to look at the dot plot from the sample, that a dot plot or box plot, or if the sample size isn't really small, a histogram, to make sure the distribution looks approximately symmetric and there are no outliers. So again, all three of those conditions were met for the experiment we just did. The samples were independent, so there's two different populations, one population for people who use the cell phone, one population for people who didn't use the cell phone. We used a random process to assign those 64 people into two groups. 32 went into one that used a cell phone, 32 went into the group that didn't use a cell phone, so we didn't try to bias the results in any fashion. And because we had a large enough sample, 32, more than 30, then that assumption was met as well. Okay, question number 3. Researchers at the University of Michigan investigated whether the font used in printed instructions influences how people think it will be to complete, how difficult people think it will be to complete a task. Participants were randomly assigned to one of two groups. Those in one group read the instructions on how to make sushi Japanese roll, make a sushi Japanese roll that were printed on an easy to read font such as Arial. And participants in the second group read the same instructions, but they were printed in a harder to read font, Mistral. All participants were then asked to say how long they thought it would take to prepare a Japanese roll according to the given instructions. The mean estimated time to prepare the sushi roll for the sample who read the instructions in Arial was 22.71 minutes, and the sample standard deviation was 13.76 minutes. The mean estimated time to prepare the sushi roll for the other sample who read the instructions in the Mistral font was 36.15 minutes, and the sample standard deviation was 15.3 minutes. For the purpose of this example, suppose the two sample sizes were both 34. So is the two sample interval, t-interval, an appropriate way to estimate the difference in mean estimated times to prepare the sushi roll between those who read the instructions in the easy read font and those who read the instructions in the hard read font? Hint, are the assumptions for the two sample t confidence interval reasonably met? Yes, one, they are independent samples from two different populations. In other words, there's no matching or paired like before, after, like this is what the person weighed before being on a diet, and this is what the person weighed after being on a diet. So they're not paired. One way to kind of test that is we really didn't need to have both sample sizes be 34. One of the samples could have been 35 and the other sample could have been 40. We don't necessarily have to choose the same number of people in each group. Two, are the samples random? It said they used a random process up here. So again, the random sample assumption is met as well. And number three, do we have a large enough sample size? And if we don't, are the population distribution somewhat normal to begin with? Because both groups had 34 people in them, which is greater than the 30, then that large enough sample size is met. Large sample size, check. Again, if it was not a large sample size, you would have to also verify that the distribution, population distribution was somewhat normal to begin with, or symmetric, and there were no outliers. So all three of these conditions are met for the experiment we just discussed. Part B, use the data analysis to calculate a 90% confidence interval for the difference in mean estimate times to prepare the sushi roll between those who read the instruction in the easy font and those who read it in the hard read font. Again, depending upon the order you want to put it in, everything would be backwards. So if the interval was positive, that means it took more time, or if it was negative, that means it took less time. So again, it just depends on how you want to orient it. So the easy to read font could be either sample 1 or sample 2, and the hard to read could be sample 1 or sample 2. You just got to keep it in the context. So again, it says go to the Shiny app we just talked about earlier, the 2 sample mean. Use the confidence and significant test tab. And here's the actual results that I copied into this lesson. And I'll show you how to get that on the app now. So let's go to the app, share the screen. I need to refresh it. Okay, for this one, the data was not coming from the textbook. We don't have the individual data, we have a summary of our data. So we're going to do summary of data. And this is a Japanese sushi roll. Okay. Group 1, the label will say this is the easy to read font, easy to read font. And group 2 is the harder to read font. Okay. And if you want to, you could say Arial and Mistral. So Arial and Mistral. Okay. And then you have to type in your summary statistics. So here's group 1 summary statistics. Here's group 2 summary statistics. Both had a sample size of 34. Sample mean For the aerial, you have to go back to your information. This was 22.7 minutes, 71 minutes, and the sample standard deviation was 13.76 minutes. For the Mistral, the average time to perform rolling the sushi roll was 36.5 minutes, and a standard deviation of 15.3 minutes. Okay, as I was typing this in, all of these formulas were being generated and changed as the numbers were entered. Again, down here by default, it defaults to 95% confidence interval, but for this example, they want us to do a 90% confidence interval, so I'm going to set it to 90. So you can see over here that for the aerial being group 1 and the Mistral being group 2, that it took on average less time to roll the sushi roll when they read the aerial font than it took for the Mistral. Remember this, the point estimate is the difference in your sample mean. So 22.71 minus 36.15 is negative 0.1344. Again, the standard error, you're going to talk about the formula of that in lesson 13. So for now, just realize the standard typical error is 3.53. And the total margin of error, where you multiply your standard error times your, in this case, your critical t-value, is plus or minus 5.89. So if you take 13.44 and subtract 5.89, you get negative 19.33. And if you take negative 13.44 and you add 5.89, you get negative 7.55. So this is all summarized on the lesson that I copied over into the lesson plan. So I'm gonna hit stop share. So you can kind of vaguely see that it says negative 19.33 and negative 7.55. So that's our confidence interval, negative 19.33, negative 7.55. So interpret the interval from part B. So again, since we're using a 90% confidence interval, we are 90% confident that the difference, or say the mean difference in rolling Japanese sushi for using the Arial font compared to the Mistral font is between negative 19.33 and negative 7.55 minutes. In other words, the group that used the Arial font on average took anywhere from 19.33 less minutes, because it's negative, to 7.55 less minutes, because again, that's negative. What does the confidence interval tell you about whether the font used in the printed instructions influences how difficult people think it is to complete the task? Again, because both of these endpoints are in the negative range, that gives us statistical evidence to conclude that it takes less time to perform this task using the Arial font than it took when you used the Mistral font. Had one of the endpoints been negative and one of them been positive, and had 0 been on that interval, then we would not have enough evidence to suggest that there's a possibility that the means are different. But because both of these guys are negative, we can now state that okay, so because the difference in means is calculated as easy to read font minus hard to read font. Again, because that's how we oriented it. We put the easy to read first minus the hard to read second, and both endpoints are negative. this indicates it takes less time for people to read the instructions in their easy to read font. This indicates it takes less time for people to complete the task with the easy to read font. Again, you can use your own words for this, but again, this is providing statistical evidence that in this case, it took less time for people to roll the sushi roll with the Arial directions as opposed to the Mistral directions. Okay, and then part E, what recommendation would you make to a company who provides printed instructions with their products based on your analysis of the data from this experiment? So hopefully from this experiment, it's obvious that you want to make sure that the instructions you provide are easy to read, so it takes less time to perform the task. So again, I'll just let you guys write that in your own words. So the recommendation is based on this experiment that you would recommend that companies use easy to read fonts in their directions as opposed to a harder to read font. All right, so I'll give you a minute to do that. And thank you for your time for lesson 12D, and we'll see you next time. Take care, everyone.